All right, let's look at some rate in, rate out problems. And this would be probably Cal 1 level stuff. It's part of the AP Calculus AB curriculum. And I'm going to use a guided notes sheet. If you want to print that, you can go to this bit.ly link and it will open up a PDF that has all of the problems and examples that I'm going to talk about in this lesson. So rate in, rate out problems have been very, very common on the AP exam in recent years. And in these problems, you are given typically two functions where one represents the rate that something is increasing and the other represents the rate that that same thing is decreasing. It does happen on occasion that you are only given one or the other. Sometimes you only have a rate in or only the rate out, but more often than not, they give you both rate in and rate out. So let's look at a couple of examples from previous years about what was provided. We're not going to work any of these, just wanted to talk about the concept of rate in and rate out. And so in 2013, FRQ number 1, we had a gravel processing plant, and they told us that gravel arrived at the processing plant by the rate given by G. And so for arriving at the rate of G, that would be your rate N. And then simultaneously, the gravel was being processed and shipped out at a constant rate of 100 tons per hour. So 100 would be the rate that the gravel was leaving. And so we had a rate in and a rate out. In 2015, we were looking at water going into a drain pipe that was partially blocked or something like that. So water went in at one rate, R of T, and it drained out of the other end at another rate, D of T. So that'll be your rate out. So we have a rate in and a rate out. And then 2009, this is a while ago, this is FRQ number 3, and we had a situation where people were entering an arena or an auditorium for a rock concert, and they said that the rate that the people entered for the rock concert was modeled by R of T, and that would be your rate in. And for this 2009 problem, there was no rate out provided. So no rate out given. That's really horrible writing in 2009. The reason there was no rate out is not that people never left, it's just that the problem, the question ended when the concert started. They didn't go all the way to the end of the concert, so they were only worried about how many people were going in to watch the concert. So no rate out was provided, but I still put it under the umbrella of rate in, rate out. And so let's talk about how we will process these problems when you see those types of prompts. And just a little generic situation, I'm going to give you two functions. We have f of t is the rate that something is increasing. And so I'm going to make a little note to myself that f of t is the rate in. And g of t is the rate that that exact same thing is decreasing. So g of t is the rate out. And I usually will make those notes to myself as I'm reading the problem for the first time, just a little bit of annotation. And rate in, rate out problems almost always eventually ask for the total number of things present. And so going back to these examples in 2013, there was a question, how much gravel is in the plant at time t equals 4? And 2009, how many people were in the arena after 1 hour? And so they will usually, if they give you a rate in and or a rate out, they will eventually ask you for the total number of people. And if they don't define that function for me, I will usually just make a note to myself that A of t will represent the total amount, and I choose A for amount. So A of t is the total amount, but sometimes they actually define that for you in the problem. So before I default to A of t, I'll skim through the problem really quickly just to see if they have defined that function for me. The total rate of change for the amount present. And so if they ask you at what rate is the number of people in the concert changing, that would be A prime, the rate of change, and it's always the rate in minus the rate out. So it's always rate in minus rate out. So in this generic example where I have F is the rate in and G is the rate out, then A prime of t would be the rate in, F of t, minus the rate out, G of t. However, there is one thing you need to be extra cautious of before you just default straight to writing A prime is F minus G, and that is that you need to make sure that F and G have the same domain. It has happened in the past that the rate in functioned on the interval like 0 to 8, but the rate out didn't start until 3 to 8. So we can't use both F and G for that window where only one of them is in operation. So always double check and make sure that your rate in and rate out have the same domain. If they do not have the same domain, then we'll have to account for that as we work through the problem. The total amount to enter, if you ever want to know how many people or how much the function has grown, well, the amount in would be the antiderivative of the rate in. And for this specific example, I did mention the domain, or the t was between 0 and 5. So I'll say 0 to 5 for this one. You could say a to b if you want to make it a little bit more generic. But the total amount to enter is the antiderivative of the rate in, and the total amount to leave similarly would be the antiderivative of the rate out. So we go 0 to 5. And if I have the rate that people are leaving, or the rate that the object is decreasing, then the total amount of decrease is the antiderivative of that rate. And then another common question is they'll ask you how many, like what is the amount of gravel in the processing plant when t equals 5 or something like that. If they want the actual amount, then my formula is going to be, and I'll say at time b. Okay, so I said time b. So I want the overall amount at time b. And so what we'll do, if we have the initial amount, so if they tell me how much is sitting there at the beginning of the time, what I need to do is I need to start with what's given. So that's my initial amount. And then I need to know how much was added and how much was subtracted, how much entered and how much left. And that's a combination of numbers 3 and 4 up here. So I need to add the antiderivative from 0 to b of f of t. That's the number of people who entered, or the number of things that entered, minus, and I need to take away the number that left. That'll be 0 to b of g of t. And what we have, that is our initial amount. That's our initial amount, plus the number that went in, minus the number out. And many, many times, I would even say more often than not, your rate in and rate out do have the same domain. And if that's true, you could rewrite this as a of 0 plus, and then because these functions have the same domain, I could write both of those up into a single antiderivative of f of t minus g of t dt. Now that's not really necessary, and I kind of lean towards doing them separately because separately always works, always, paying attention to the domains. Putting them together as a single antiderivative will only work if the two functions have the same domain. So just something to be aware of. And let's look at a very specific example. This is from 2005. That's quite a while ago. Goodness, that's 20 years ago. We have a function here that says tide removes sand from a beach at a function given by this. A pumping station adds sand by the function given by that. It says S and T have units of cubic yards per hour. Hours, it looks like they're both in operation at the same time, so it looks like they have the same domain. And then we have some initial condition at time 0. The beach contains 2,500 cubic yards of sand. First thing I will do, because I don't like reading a block of text when I'm doing math work, is I will go through this problem and I'm going to remove all of the important pieces, or at least what I think will be the important pieces. And the important pieces are that I have a rate, let's see, R of t is the rate that sand is removed, so that's my rate out. So my rate out is R of t. My rate in, pumping station adds sand at the function S of t. Let's see, my domain is 0 to 6. I don't think we're going to make an extra note of that. Oh, here, initial condition. At time 0, the beach contains 2,500 cubic yards of sand. There's an initial amount. Now, that's not a rate. That is a raw amount of sand that we started with at the beginning of this little situation. And I usually will write something like A of t is the amount of sand. I like to define my function. If you're going to create a function for a problem, you need to thoroughly define it. So A of t is the amount of sand in cubic yards at time t. And they are telling us that the amount of sand at time 0 is 2,500. So I have that initial condition. Cool, so I have that. And then I think that's all I need for now. I think that's all I need. Let's look at the problem here. So how much sand will the tide remove? So how much will be removed? How much sand is being removed? That is only a function of the rate out. However much is being added is irrelevant. We're only talking about how much is being removed. Well, I have the rate that the sand is being removed. If I want the amount that is removed, I need to do the antiderivative of the rate that sand is removed, and we'll evaluate this from 0 to 6. And I'm looking at this rate out function, and you should be able to find that antiderivative. This is a u sub antiderivative, and you should be able to do that by hand. However, on these rate in, rate out problems, they are almost always, there are very few exceptions, almost always a calculator problem. So I'm going to go to my calculator, and I'm going to start defining my functions and getting my calculator primed and ready to go. So here's my calculator. I like to use the TI Inspire, and so I'm going to start by defining my function r of t, and the way you do that in the calculator is you do r of t, and then above this little button right here next to the 9, colon equals, and then you just type in the equation, and that's 2 plus 5 sine of 4 pi over 25. So 2 plus 5 sine of 4 pi, so I'm going to do control divide, 4 pi over 25. Always double and triple check that you plug that you store things correctly. I'm going to hit enter, and it says done, and I'm going to repeat the exact same thing for my rate in. Give me a second to do that. Okay, and I have stored that function, and as I was entering them, I was double checking myself for common mistakes, and one common mistake is obviously just not entering the function correctly, like putting a minus where it should be a plus or something careless like that. Another common mistake, I've defined these as r of t, r of s of t, and some people write like s of t but then put x's in the formula, and that really throws it off. So you want to make sure that you stick with the correct variable, and as I was double checking r of t, I noticed there is no t at all. That is currently a constant because there's no t, and I went back and I double checked the problem, and on the problem there's no t there either, and that was a typo, so we need to go back and fix that. This is going to be the function 4 pi. We need to inject a t right there. I double checked that. I went back and looked at the College Board's website, and there should have been a t there. So I need to go back and fix that, and I'll do that in just a second. And I want to show you one thing. When you need to correct something like this, quick ways to do that is if you arrow up, it will highlight previous entries one at a time. While the one that I want to edit is highlighted, I hit enter, and on the Inspire, that will copy it down to an editable line, and I'll just arrow back, and I'll enter a t here. I'm going to put times t. I like the multiplication sign. Enter. And that will overwrite what was previously stored for r. You don't need to clear the first r and then store it again. You can just overwrite what was previously there. So I now have my r and my s defined. And finally, back to A, how much sand will the tide remove? I need to do the antiderivative of r of t from 0 to 6, and we will simply punch that in the calculator. Where's my calculator? There he is. So I'll do a shift plus, hot button for antiderivatives. And my function is stored for r of t dt, and I'm going to hit control enter to force the decimal, and I'm getting 31.8159, and we are just punching that straight into the calculator. 31.8, I forgot what it was, 8159. And the reason I'm going 4 decimals instead of your standard 3 is because on the AP exam, you must be accurate to the 3rd decimal. If you include more than that, that is okay. And in this case, indicate units of measure. Let me write that. So that's going to be the amount of sand will be measured in yards cubed. And in this case, they would actually accept 2 rounding answers. They would accept 31.816 following standard rounding procedures, or they accept what is called the truncated version, where you simply write what you see for the first 3 decimals and you stop. Now, I already have units written, but it's bugging me not writing it again. All right, so there we go. The amount of sand that has entered would be 31.815 yards cubed, so that we know that's how much went into, wait, that's how much was removed. That's how much was removed. So let's see, moving on. Write an expression for y of t, the total number of cubic yards of sand. Dadgummit. I even said I would do this. I should have done this earlier. Not a big deal, but y of t, the total number of cubic yards, that's what I defined as A of t. So I'm actually just going to go back to my previous work. Since they have defined this as y, I guess I'll call this y. Y of t is the total amount of sand in cubic yards. And I know the initial condition is y of 0. And the way we'll do this one is we're going to go back to this formula right here, number 5. If I want the amount of sand at any given time, it's your initial amount plus the amount that went in minus the amount that went out. And we'll do that in this problem, y of t is your initial amount, y of 0, plus the antiderivative from my initial point in time to some unknown time of my rate n, which was s of t, and that gives me my amount n, minus the antiderivative from 0 to some unknown point in time of r of t, and that is the amount that left, the amount out. So I have my initial amount plus what went in minus what went out, but obviously cannot leave answers with question marks like that. So I want the amount of sand at any point in time t, which means this upper limit needs to be some unknown value of t. Now, I will say typically they don't ask you for the generic function like this in terms of t. They usually will say find the total number of cubic yards on the beach at time t equals 4. They'll give you a specific time, in which case you would do 0 to 4 for both of these integrals. However, they did want an expression. And a point of emphasis here, while this could be considered correct, I don't like having the same variable for my upper limit of integration as I do my lower limit as I do my function that's in my integral. So instead of doing s of t dt, I just throw in a dummy variable, and I'm just going to replace these t's for x, because t is defined as the time at which I'm interested in finding the total amount of sand. So that needs to be the upper limit, which means any other t does not need to be confused for that same time. So I'm just going to replace them with any other variable, and I'll replace them with x. And that would be an expression. I think that would be acceptable. However, we do know that at time 0, there were 2,500 cubic yards of sand, and because S and R are both operating on the same domain, I can combine the amount in and the amount out as a single antiderivative. So I could do 0 to t of the amount in, S of x, minus the amount out, R of x, dx. Cool. So there's your setup. That's it. That's all we have to do for number B. Find the rate at which the total amount of sand is changing at t equals 4. All of this, everything after the word find, all of that, the rate at which the total amount of sand is changing at time t equals 4, all of that is the exact same thing as saying find y prime of 4. The overall change, and in this case, and I mentioned this earlier, the overall change is always the rate in minus the rate out, and we're looking specifically at t equals 4. Well, my rate in is the function s at 4 minus my rate out, which is my function r at 4, and I have both s and r defined in my calculator, so I'll go back to my calculator, and I need to do s of 4 minus r of 4, and again I'm going to hit Control Enter to force the decimal, and I'm getting negative 1.9087. Negative 1.9087, which again, that could be rounded up, negative 1.909, or they would accept that as negative 1.908. And they don't ask you to interpret this or anything like that, but the fact that the overall rate of change is negative means that at this current point in time, the amount of sand on the beach is indeed decreasing. We have a negative derivative. Now that I'm just going overkill there. They don't ask for units. They don't ask for an interpretation. They just want the number. So there's the number. And let's look at part D. And what I have for part D here, what they put in part D, is extremely common on these rate in, rate outs. They very, very frequently will ask you when the amount of sand is at a minimum and or at a maximum. In this case, they're asking for the minimum. And this particular problem says for T, for 0 to 6, we're on a closed interval. We want a minimum on a closed interval. This is an extreme value theorem question. And when you're considering the extreme value theorem, you need critical numbers of your function. In this case, we're talking about the total amount of sand. So my critical numbers would be when the derivative of the total amount of sand, y prime, is equal to 0. And we already know that y prime is the same thing as s of t minus r of t, because the overall rate of change is always rate in minus rate out, which means I need to find out when s of t and r of t are the same. That will give me my critical numbers. And I also need to consider the endpoints. My endpoints are explicitly given. That's t equals 0 and 6. And so let's get those critical numbers. And this is a calculator problem. So we're going to solve this on the calculator, and I'm going to solve it graphically. So I'm going to go to my graph screen. And because I have these functions stored for s of t and r of t, I can graph them here. But do remember, on your graph screen, everything must be in terms of x. So I'm going to write s of x. And there's my graph for s of x. Let's type in r of x. Enter. And I am interested in the interval 0 to 6. I'm going to edit my window to go from 0 to 6. And I see a single critical number right there. So I'm going to go menu, analyze, intersection. I have that intersection is 5.1178. It's getting kind of long. I didn't think this would be this long of a video. So there's my critical number, and I'm going to store that. That is an intermediate answer. That is not a final answer. So I'm going to go to my calculator. I'm going to click on that x coordinate. I'm going to hit Control Store, and I will store that for A. So my critical number is now stored for A. I'm going to go back here, and I'm just going to say, make a little note here. Let's let A equal 5.11, and I'll round that up, 5.118. So I have my candidates. I have my endpoints, I have my critical number. Now we need to determine at what time do we actually have the minimum. And in the extreme value theorem, to determine which one produces the minimum and the maximum and all that mess, we simply plug those candidates into my function, which is y of t. I need y of 0. Oh, that was given. That's 2,500. That's cute. I need my total amount at time critical number, and since I have denoted that A is the same thing as 5.118, I can actually write y of A. And then I need y of 6. And how am I going to get those values? Well, we can go back to our answer for part B. We have a function right here that provides total amounts at any given time. So we're going to use that expression for D. And so I'll do that very quickly. I'll write the first one. Hang tight just a second. There we go. I went ahead and wrote both of them. So I simply replaced that upper limit of t with the values that I'm trying to figure out the amount of sand. So I have my endpoints of 0 and 6, my critical number of A, and then we'll go to the calculator and I'll punch these in the calculator, which I'll do in just a second. Okay, almost done. So there I just plugged them both in, and we got 2492 and 2493 plus some decimals, and so I've already written that here. And so now we are looking for the minimum, and make sure you answer the question. This asks for two things: at what time t does the minimum occur, and what is that minimum value? And so the minimum amount, the minimum is, and the actual minimum value is 2492.369. And that will be in cubic yards. They don't ask for units, but I'll feel good putting units. And that occurs at time t equals, and that critical number was 5.118. And there is your final answer. It does say to justify your answer in extreme value theorem situations. The justification is the body of work that we used, finding the critical numbers, showing that we evaluated all the candidates, and then analyzing which one is either the largest or the smallest. And I'm so sorry this got so long, but I'm going to quit here. Yay!